welcome back to Decaf-Math ASMR, and a very warm welcome if you are new. I hope that you are doing very well and that you are ready to relax with a bit of math. I'm excited today because we get to revisit differential equations. A little bit of differential equations. Diffy Q. And we are going to take a look at a particular type of first order differential equation called the Bernoulli Equation. Bernoulli Equations. And we are going to look at a particular method, substitution method, to help us solve these kinds of equations. And it's just really cool how it all works out. So, as usual, it doesn't matter whether or not you're actually learning this stuff. If you are, I hope that it is helpful. And usually, you learn about linear first order diffy-Qs first. So using integrating factors. I don't think we've talked about that here on this channel. But we do assume that we know how to do that for Bernoulli equations. So we usually learn those first. But we can, of course, come back to it. But either way, I do hope that this is cool, and there's also a little bit of Calc 1 stuff for those of you who really like derivatives. So what we'll do is go over what Bernoulli equation looks like, what it is, and then kind of talk about the substitution that helps us simplify the problem, and maybe even try to work through an entire problem from beginning to end. So let's relax and begin. So a Bernoulli equation is first order, like we said, which means that we'll have a first derivative, so a dy dx. Remember that in general, differential equations are just equations that have derivatives in them, in the most general sense. Some of them, even the ones from calculus, where we just have dy dx equals, x squared. When we first learn about integrals and stuff, we have methods to solve. So that's technically a differential equation because there's a derivative in it, and it literally has an equation, or it literally is an equation. But we also learn about more complicated type of problems. Now, some of them we can learn and solve, like some first order diffy-Qs or second order diffy-Qs, but there are also plenty of diffy-Qs that we cannot solve, unfortunately, and in those we're just gonna have to use approximation methods and stuff like that. So there's not always, a direct way to calculate them. But this happens to be a method that we can. So we'll have our first derivative, and a lot of times in physics, we have derivatives with respect to time, so t, but we're going to keep it classic and basic for now, so dy and x, y and x, y and x. So if we have this equals p of x times y plus q of x times y to the n, where n is any number as long as it's not 0 or 1. Then this entire thing is called a Bernoulli equation. And sometimes you'll have a problem that kind of looks like this. It's like a Bernoulli equation, but kind of hidden. And that is okay. You're gonna have to mess with it a little bit, use some algebra to work with it, but if you can in general get it into this form, then you have yourself a Bernoulli. Excellent, excellent, excellent. Okay, so let's look at why n can't be 0 and 1, because that seems kind of random, right? Well, if n is 0, then we have y to the 0, which is 1. Anything to the power of 0 is 1. Anything times 1 is itself. So this would go away and we'd just have q of x. If that is the case, then that is actually just a linear first order problem. We have the derivative, we have the y, and then we just have q of x. So we actually would already have a method for that, and that's just the linear case with the integrating factor. So that's not a Bernoulli equation. And if n is 1, then we would have y to the 1 here, which is just y. Anything to the 1 is itself. And then that would leave us with p of x times y and q of x times y, which we could combine and factor out a y. So we could do p of x plus q of x parentheses times y. And since those are multiplied, that actually makes this equation separable, which just means we can put all the y terms on one side, all the x terms on the other. It's just multiplication or division. So we could go ahead and take the integral on both sides and solve directly there. So we also would have a method for that case, and that is also not a Bernoulli equation. So these are like the special cases. You know, the 0 and the 1 are the special cases. So as long as n is not 0 or 1, we have a Bernoulli equation. Okay, now I also wanted to mention that, you know, if you see this written, you know, from different resources, you might see it written slightly differently. I think this is the most common standard form, but, you know, math should be a universal language, so it shouldn't actually matter, and hopefully anything that you see is equivalent to this. But for example, you might see y prime instead of dy dx, as long as you are clear with the original. Like when you use primes, you're using the derivative with respect to your original variable, and just make sure you know what variable that is, as long as you're consistent. And also you might see this part with the y on this side. So some people like to have the q of x, y to the n part on the right side alone, and just do like y prime, maybe like plus a of x times y equals b of x times, or equals, yeah, b of x times y to the n. So that's arbitrary. P and Q and A and B and F and G, whatever you want, are arbitrary. Just the general idea is to have a derivative, some function of x with the y, and then some function with the y to the n that's not 0 or 1. And the reason that if you have the plus a of x and y on this side, the reason those are equivalent is because even if you look at this and you move this to the left side, so you have a minus p of x, y, the minus doesn't really matter because minus p of x is also going to be a function of x still, just you happen to be negative every term. So you could just replace negative p of x with a of x or whatever, and so plus a of x. So remember, we're just looking at the big picture here. The details with the negative p of x doesn't actually matter. So you just want to have these pieces, and if you see these elements, then that can kind of clue you in that you're working with Bernoulli. And so if you have some function of x here in front, that's okay. You can just divide it through. You know, like I said, you might have to do a little bit of algebra to make it look like this, but if you have these elements, you are most likely looking at a Bernoulli, okay? Good. So now then we have a method to help us solve this kind of question. Now that we know it's not linear and it's not separable, what can we do? We can carry out a substitution. Specifically, it allows us to change the variable, kind of like making a u substitution. And in calc, right? So we would change the variable from x to u, and our incentive for that is that sometimes if we carry the entire substitution out, it makes the whole problem simpler, and it makes it something that we already know how to solve. And then we can use that new variable and solve it the way that we know how, and then use the substitution to carry us back to the original variable. So it really just comes down to being clever in the substitution that we pick. Because remember, when we did u sub, it's arbitrary. Well, it's not arbitrary, but it could be arbitrary, right? U can be anything that you want it to be. It's just a little tool to help us simplify things, hopefully. But you know, depending on what you pick, sometimes it doesn't take us anywhere. So that's why we want to kind of be clever in what we decide, right? So in this particular case, there is a special substitution that does make our life much easier, and that is to let whatever your variable is, v, z, w, whatever you want. I usually use v, to equal y to the 1 minus n. Y to the 1 minus n. Now you can memorize this if you like. But I'll kind of show you why you don't have to. And it also is kind of time consuming, because if this is all that you memorize, then you actually have to carry out the derivative every single time, and that might just be kind of tedious, depending on what your n is. So the general idea is that our goal for this substitution is to turn this entire equation into a linear first order one, which we know how to solve with an integrating factor, or we can solve with an integrating factor. And we want it to be in terms of v. So if this thing can somehow be equivalent to a linear first order one in terms of v, then we can use our methods to find the solution for v, and then use the substitution back to find y again. And the reason that this is really clever, this one, to build a little bit of intuition, but what I'll actually show that it is indeed linear, this is really cool because if we just take this formula and divide all the way through by y to the n, then you can kind of see we'll have to work with this part, but even just this piece alone, if we have divide by y to the n on both sides, you have to divide, distribute each term. So we'd have stuff with y divided by y to the n, and using our exponent rules, that's going to be y to the 1 over y to the n, so y to the 1 minus n, which is exactly this y to the 1 minus n. So this term is going to turn into something v, which is great, and then this, dividing by y to the n, is going to make that go away, and you're just going to have a q of x, you're going to have a function of x. So that's great. That's part of our linear thing. So all we're really looking for now is that this thing is something to do with v prime. We have a v and we have a q of x, so we want something to do with v prime, and of course some kind of function of x here. So that's what we're actually going to derive, but that's kind of why setting v just sort of intuitively to equal y to the 1 minus n, it really just comes from dividing both sides by y to the n, and that's actually the first step that I would suggest memorizing rather than just the substitution. I recommend remembering for Bernoulli to just divide by y to the n on both sides, and you'll get to the same thing. So it'll make more sense when we have like a specific function of x here and here, but just wanted to point that that out. So then if we let this substitution happen, then let's actually show kind of like what we were saying here, but let's actually directly carry out the substitution to show that this will be a first order linear equation indeed for any case. So in order to do that, we want to take care of this dy dx part, which is y prime, right? And we'll want to convert that into something to do with v prime or dv dx. So, because we want to, our goal is to get rid of all of the stuff with y and replace it only with v, and look at what happens. So to do dv dx, those of you who love derivatives from calc might recognize this. This is our chain rule, chain rule. And we need that because v is a function of y here as written, but y is a function of x. Y is a function of x, that's what we're working with here. And so we can take the normal derivative, so to speak, but then we also need to do chain rule, chain on the dy dx as well. So we have our v prime, if you want to write it as that, it's our original variable, so that's just v prime. And now we just have to carry out the derivative of each piece. So dv dy is this derivative, which is just our power rule. We have y to the stuff, so we just move that to the front. So 1 minus n times, you keep your thing, and then you do one less, right? 1 minus n minus 1. Because in general, if you're taking the derivative of like x to the n, you have nx to the n minus 1. So 1 minus n minus 1 gives you negative n, and then you just have your dy dx. Excellent. There's your dv dx. And so that's our dy dx right here. Or you can just write it as y prime, right? But in order to make the direct substitution, we'll want dy dx in terms of dv dx. So I'm just going to go ahead and write this as v prime. So 1 minus n. Put this negative exponent down here times y prime. So in order to do y prime in terms of v prime, we just flip-flop. We divide by, or you can multiply by y to the n divided by 1 minus n times v prime. So that's the other half of the substitution that we need to do to get this thing, which you'll see we have y prime and v prime here. So that's awesome. That's exactly what we're looking for, right? So now with all of these pieces, let's see what we can get and see if it's actually a linear first order equation. So we have y to the n divided by 1 minus n times v prime. So we're just going to go ahead and make that substitution equals, and then I'm just going to keep everything else the same for now. So we still have some y's that we're hoping to get rid of. Okay, so now we just need to, in order to make this kind of parallel to this, we have our v prime or dv dx, and then we want it to equal this stuff. So that means we want to get rid of this first part. We want to get rid of that, and we can just do that by multiplying by the reciprocal on both sides. Meaning just this will cancel with this, but we have to multiply that factor by each piece, right? Kind of distributing it across the entire equation, dividing both sides, however you like to think about it. So in order to do that, we get v prime, that isolates our dv dx, equals, and then we have 1 minus n times p of x, and then we have our y over y to the n, which which we said earlier is y to the 1 minus n. Conveniently. Coincidence? I think not. So then we also have plus, and then 1 minus n, which is just a number, times q of x. And then the y to the n divided by y to the n goes away. That's 1, so that goes away. And that is exactly why. Now this thing is going to be just the number times a function of x, which is going to be a function of x as well. And then y to the 1 minus n is the substitution for v. So this piece is actually v. So in the end, we have v prime, which is dv dx, equals 1 minus n p of x, which is just stuff, a function of x, times v plus 1 minus n q of x. And that is indeed first order linear, because we have a v prime, we have a v, and then we just have a function of x, and this is a function of x. And so this is similar to this, but we essentially got rid of the y to the n part, and now instead have this. So this is linear now, and we can use the integrating factor to solve whatever we translated it into, to solve that for v, and then plug back into y to the 1 minus n to solve for y. So that's the general idea. What on earth did we just do? We just proved that the substitution v equals y to the 1 minus n allows us to translate this entire equation into stuff with just v's. And when we carry that derivative out here, we get a messy equation, but really a linear first order differential equation in terms of v, which we can then solve and then plug in to solve for y. So this will make much more sense when we work through a specific example. But I think I'm going to go ahead and make that a part 2 to this video, and that way we can kind of let this sink in a little bit and kind of replay it a little bit. Don't get too bogged down in the actual substitution here. Like I said, if you want to do this every single time, you can, but this is a lot to memorize. It's more than just memorizing v equals y to the 1 minus n. But that's really what the general idea is. That's what we're actually after. So then we can go ahead and instead, if you just have a general problem that you're trying to solve, go ahead and divide through by y to the n. So if you have like y to the 5, just divide by y to the 5 all the way through. Or let the substitution be let v equals y to the negative 4. But you don't have to memorize all this other stuff, okay? It's just good to see that it actually does turn it into a first order equation. So keep an eye out for our practice problem. And I hope that you enjoyed letting the math kind of just wash around you. Wash around you. Thank you so much for hanging out with me today. And we'll see if we can kind of carry out, especially the problem might get a little bit longer because we do have to use the integrating factor as well. So that might be a good review for that part as well. So that's what I meant by wanting to start with the Bernoulli and then do the substitution and then carry out the integrating factor part and then going back. But I will see you around for more math very, very soon. Take good care of yourself and much love.